So that's, the 7 takes care of the first position, but what about for the remaining n minus 1 digits? Exactly, you just basically have h sub n minus 1 ways to finish writing that out. So there are that many ways to get a valid code word. You know, that should probably be explained a little bit. I'm going to move case 2 to the other board in a second. I need a little bit more room here. So the idea here, just to explain this, is that you have 7 choices for the first digit, right? And then the remaining digits must have an even number of 7s, and there's of course n minus 1 remaining digits. So that would be how to do that part. And then I have to do case 2. So for case 2, first digit does equal 7. How many ways will there be in this case? You guys kind of did this on the quiz already. So you start with a 7, for sure. You have no choices about that, by the way. You're not making a choice right there. That 7 that I wrote down is not how many choices there are. That's the digit that you're putting in that slot. So what about the rest of the unknown positions in that code word? Are you forced to put another? Well, you will be forced to put another 7 in there somewhere. Does it have to be in the next position? Not necessarily. How do we handle this case? We have n minus 1 more spaces. The point, yeah, that's the point. I think that's what you were going to say, Jeff, that the remaining spaces have to have an odd number of 7s because you've got a 7 already put into the first spot. So the n minus 1 unknown spaces have to have an odd number of 7s. So let me just indicate that here. Must use odd number of 7. Well, how many strings, do we know how many strings of length n minus 1 have an odd number of 7? Did somebody have the answer? How many is it, Peter?
What?
Oh, you just said you had the answer, I thought. Let me ask the question again, make sure everybody understood the question. How many strings of length n minus 1 are there that have an odd number of 7s?
3 to the n minus 1. Oh, 8 to the n minus 1 minus a sub n minus 1. Or you use h or n?
8 to the n minus 1 minus, what was that?
H sub n minus 1.
That's the answer.
Inclusion exclusion.
It's the subtraction rule, right? The strings that have an odd number of 7s are actually what we are not trying to count, right? So what Peter did, well, I'll let him tell me. Where is this coming from?
You have 8 choices for all the previous ones.
So 8 choices because the total number of digits available is 8, right? So you have 8 choices, 8 choices, 8 choices. What Peter did is he just figured out how many total number of ways are there to write down a string of length n minus 1. And it's 8 to the n minus 1. And then he took out the strings that have an even number of 7s. And that leaves you, of course, with the number of strings with an odd number of 7s, right? So this right here is equal to the number of code words, I guess I could call them. Code words of length n minus 1 with an odd number of 7s. Okay? Because you take, this is just the total strings of length n minus 1. Guys, you can't just completely forget about the counting stuff for this material. You've got to still be able to do some of these things, even though this test is more focused on the later material. The h sub n minus 1 is strings with even number of 7s. And that leaves you with the strings with an odd number of 7s. Okay, can anything else happen? So there's no other cases, right? And these two cases are mutually exclusive, right? This is what you always want. You want cases that are mutually exclusive, that are complete and cover all possible scenarios. And that's what you have. The first digit of your code word either isn't a 7 or it is a 7. It's got to be one or the other. So what do we do next? Add them together, exactly. And that's going to give you the recurrence relation for h sub n. So it's going to be 7 times h sub n minus 1 plus 8 to the n minus 1 minus h sub n minus 1. Okay? And that adds up to 6 times h sub n minus 1 plus 8 to the n minus 1. And that is your recurrence relation. What is the order of that recurrence relation? It's just 1, right? It's just 1. Is it homogeneous? No, it's actually non-homogeneous, okay? So that means we actually have to do a longer process to come up with the solution. But let's do that later. Let's just start with the basic stuff first. How many initial conditions should I find? It's only a first order recurrence relation, so you really only need one initial condition. So the initial condition would be what value of n? 1 would be the shortest code word you could make. So that's my question. What is h sub 1? How many valid code words of length 1 are there? The one digit that you write down can be anything except a 7, right? Because if you had a code word of length 1 that was a 7, then that would be an odd number of 7s, and that's not what you want. So you have any other number available to you. So h sub 1 should then equal to 7. Clear enough? All right, so we got that, and now we just have to solve this. You remember the process? What's the first thing? Solve the corresponding homogeneous recurrence relation first. So to solve, we have 3 steps. First step is solve, in this case, h sub n equals 6 times h sub n minus 1. What's the characteristic equation for this? Okay, it's real easy, right? X is equal to 6, right? So what is my homogeneous, I'm going to use a super H on this term. What is my homogeneous component of my general solution? Yeah. Just that, right? That's all you got to do. C1 times 6 to the n. All right, we got that down.
We don't solve for C1.
Okay, this is an important point. Thank you, Lisa, for bringing that up. This is not the time to solve for C1. Okay, because the thing is, yes, you have an initial condition here, but the initial condition is going to be used at the very end of the problem. So we will come back to this at the very end in order to figure out what C1 is. If we try to solve for it right now, we're not ready to solve for it because we still have to find the second part of the solution. Okay, the step 2, which is the particular solution. So we just start like that. Just get the homogeneous piece down. Okay, what about step 2? What was step 2? Can anybody remind me? Solve for the particular solution. So, and do you remember how we do that? Yes. Right. So we make a guess, and the guess of what the particular solution is based on what? we go back to the equation, right, and we look at the form of this non-homogeneous piece. And in class, we went over how to handle polynomials and power functions. So you should be able to do them both. This is obviously a power function, 8 to the n minus 1. Now some people were getting, okay, so basically we make a guess. Let's guess that the particular solution, which I'm going to write as h sub n of p, I'm going to guess that this is equal to, if you remember from the notes, the way that you make the guess is you put some constant p there times 8 to the n minus 1. I'm trying to remember, did I use a p for that or some other letter?
Yeah.
Oh, I used a d. Okay, I'm sorry. I may not have been totally consistent. It doesn't matter.
For the polynomial.
Huh?
You use D for the polynomial.
Oh,
What did I use for this?
You
you didn't use times 8 to the end.
Yeah, we didn't practice that.
We did it for our homework.
Oh, in class I did a polynomial one. And I used d, like d naught plus
Yeah.
d1x plus d2x. Okay, that's fine. So we didn't, so I never did this?
No.
Oh, okay.
So-
I thought I did.
It's
Um,
P, had it on our quiz.
And it was on our homework.
All right, so you know, the point I'm trying to make is, I thought I did an example of each one. Maybe not at the same time. I thought maybe later I went back to it, but who knows? My mind is a fog right now. Just so you know, if there's, say, something like that, this came up, I know, on the homework. There was a constant sitting out in front of this power function. Don't let that mess you up. You still use the same guess here. The same guess will work. So it's just a constant times a power function. Yeah, go ahead, Nicole.
Are we able to guess p times 8 to the n, or does it have to be 8 to the n minus 1?
It could be 8 to the n as well, because see, the thing is, here, I'll just show you. This is the same as that, and then I can just say p over 8. I'm just going to call it p prime now.
Okay.
So you can do that too. Yep. Or,
By the same reason, we could have left the constant also, the 3 that we put, the 3 times.
yeah. Okay. So if there's a 3 here, exactly. Then if you want to put the 3 here, it's not wrong. This is the point I'm trying to make: is the constant that you put in front of this power function doesn't actually matter. Doesn't matter. It'll get absorbed into the calculation, and we'll all end up with the right answer at the end of the day, no matter what we chose to start with. So I'm going to take it out of here because I don't want to confuse you, and I think I'll take it out of here too. So are you guys okay if I just use p times 8 to the n minus 1? Okay, let's just do that. And then we just do what with that?
Substitute it into.
Yeah, you just plug it into your recurrence relation on both sides. So on the left side, so plug into the relation. On the left side, that will give me h sub n, so it's p times 8 to the n minus 1 equals, on the right side, I get 6 times h sub n minus 1, which will be p times 8 to the n minus 2, plus 8 to the n minus 1, right? Okay? And from there, I'm just trying to solve this for p. So I can cancel a lot of factors of 8 from everything. Let me do that first. I'm going to cancel I'm going to cancel n minus 2 factors of 8 from this whole thing. And that's going to leave me with 8p equals 6p plus 8, I believe. Right? And subtracting it over, you're just going to get p is equal to 4. I did it right? P is equal to 4. And so that means that my particular solution is 4 times 8 to the n minus 1. Yeah? I'm not getting a whole lot of confirmation here. Guys, remember, I stayed up till 4 in the morning 2 nights ago, and until 2 in the morning last night. I could very easily have something that needs to be corrected here. So just let me know. It's probably my fault if something's wrong. Is everything okay?
Yes.
Okay, good. I got at least 2 people saying yes now. All right, so I'm going to take this as this is right, and we have this is the homogeneous piece. So what's step 3, our third and final step? Add them together. So the homogeneous, the overall solution for Hn is C1 times 6 to the n plus 4 times 8 to the n minus 1. Am I done? No, what else do I need to do? Now I use the initial condition to find what C1 is. Okay, so let's do that. I know that 7, which is what H1 is, should be what I get when I evaluate n equal to 1. So when I plug in n equal to 1, I get 6C1 plus 4. So C1 looks like it's going to be 1 half, yeah? C1 is 1 half. Okay, good. So let's write down the final answer. Final answer. This thing is that camera still going?
Oh yeah, it beeped a while back, but I.
You started it again?
Yeah.
Okay, good, because every 30 minutes it shuts off. Okay. At some point the battery will die, and I have another battery, so we'll just switch it out.
Yeah, it's getting there. Last
Okay.
bar.
You're watching it for me. Okay, so C1 is equal to, we said it right here, C1 is equal to 1 half. So my final answer is Hn equals 1 half times 6 to the n plus 4 times 8 to the n minus 1. Okay? Honestly, so Nicole, for example, or anybody really who may have started with something different up here. If you had started this with p times 8 to the n, you're going to get the right answer. You might get a different value for p, right? But it wouldn't be a bad idea to work it through with your calculation and convince yourself, yeah, at the end of the day, you do have the same answer on the board. So it should be okay. Everybody all right with that? What do I do with my... Oh, here it is. Yeah, that's exactly the answer I got. Okay, ready for another one? So far, reasonable? Not too bad. I mean, again, you can go back and you can think about modifying this question. Like, pretend like you're me and you're writing a test now. I mean, could you ask something that would be like a variation of this question? What if you have to have an even number of 7s and an even number of 6s? Or some weird thing like that. Don't want to do it?
Every number that appears must have an even number. So.
Yeah, that's like the fully extended version of the question. So, I mean, there's other things you can, there's easy way, you guys, that's the thing with combinatorics, it's easy to write these questions. And you just, to modify them and to come up with things, so don't just answer the questions, ask questions. And see if you can work them out. There's no end, all right? No end to how many you can ask. Let's go on to problem number 3 for now. All right, so problem number 3 is this. How many ways are there to select n flags if the number of green flags is at most 1, the number of yellow flags is 0 or 2. So we have at most 1 green flag, 0 or 2 yellow flags, and the number of red flags is a multiple of 4.
Are these the only three colors?
And these are the only 3 colors, yeah. So don't say anything yet. I want to let everybody think about that while I erase the board, and then we will talk about it. Does anybody think that they know the approach to use to solve this? Only 2 people? Rocky, have you ever seen a problem like this before?
Yeah, use generating.
Okay. You just wanted to let everybody else have the glory. Okay. Yeah, we're going to use generating functions to solve this one. Basically, the way you want to do it is you want to create a power series or a generating function whose coefficients are precisely the number of ways to select the various numbers of flags. So let's just say the ways to select n flags, that's just h sub n again. Okay, so we're just gonna kind of go with it in that context. Does that make sense? Okay, does anybody know how to write down the generating function or how we would do it? Mark, do you know how to write down the generating function for something like this? There's 3 different parts to it. Yeah. So let's see if we can do it. We write a generating function for h sub n. Remember, a generating function is basically, when I say that, what I mean is we're going to write a power series, I call it g of x, and it's got a constant term which is called h0. And it has an x term, which is h1, and an x squared term, which is h2, and so on. And it, in theory, goes on forever. And the coefficients in front of these powers of x are exactly the numbers of ways of selecting the number of flags that we're talking about. Okay. So how do we do it, though, for this particular set of conditions over here? Peter, do you know?
Yeah. Wait.
Then let's hear it. What'd you come up with?
Well, for the red, multiple 4, you can have 1 plus x to the 4 plus x to the 8, blah, blah, blah.
Okay.
And then the 0 or 2, then you would have just 1 plus x squared.
So what do I do with that?
That is just 1.
Is this another term?
Uh-huh. Multiply.
Okay. So by the way, just so you know, terms are always added together, and when I multiply expressions together, what do we call those? For all you future teachers out there. Starts with an F. Factors, yes. So terms and factors. Factors. So if it's a factor, I multiply it by. Sorry, I'm a little bit of a stickler on that. What is a term? What is a factor? So factors are multiplied together. So this part here is just for the red.
Right.
Okay, so then what's the rest of it, Peter? Go ahead.
Not the yellow, so 0 or 2, so just 1 plus x squared.
Okay.
And then for the, what were we?
Green is at most 1.
What is the green?
That's the first part.
Oh, okay. At most 1. So you have just 1 plus x.
Okay, good. And you just multiply these, right?
Oh, yeah, you go down backwards.
That's all right. So we just do it like that. Okay. So basically, when you FOIL this out, right? Imagine foiling it out. When you FOIL it out, it's like picking one of these terms, one of these terms, and one of these terms. Which really means you're picking how many red flags, how many yellow flags, and how many green flags. Those are the exponents, right? The exponents are telling you how many of each type of flag are you choosing. So if I want 4 red flags, 2 yellow flags, and 1 green flag, that would be like picking the x to the 4th, the x squared, and the x. And that would be a total of 7 flags. And that would be one way to get x to the 7th out of that. Okay. So this is great, we wrote down the generating function, but does this answer the question yet? This is a generating function for h sub n, but we still have to find h sub n, because that's what the question is asking. So that means we have to do what from here? Find a closed form, is that what you said, Anthony?
Good job, man.
What does that mean? What's wrong with the form that we have now?
The red can be simplified. Yeah.
Hmm?
The red can be rewritten as 1 over 1 minus x.
Yeah, guys, these infinite power series, these basically these geometric series, you have to make sure you know. So this is something for Monday. Everybody has to know. 1 over 1 minus x is the same as 1 plus x squared plus x cubed. That's sort of the starting point for a lot of the series that you come up with. You'll remember that we have sometimes had to start with that 1 over 1 minus x and do something to it, like take a derivative or multiply it through by a constant or something like that. If this is not sounding pleasant to you, you've got to go back and review those problems that you did in the homework on it. Or I even had this on the quiz a little bit. This kind of expression is very easy to simplify, and everybody just needs to make sure they know how to do that. So for instance, this red piece right here, this is really just the same. This is like 1 plus y squared plus y cubed and so on. It's the standard power series, the #1 most important power series in the whole world, except that I've replaced the x with x to the 4th. So this becomes 1 over 1 minus x to the 4th times 1 plus x squared times 1 plus x. The second and third factor don't bother me because they are finite. Okay, is this, Anthony, I think I got your closed form for you. Is that right? Is that what you wanted me to do? No, that is the closed form. That is the closed form for it, but am I done with working with that? I don't have the answer to my question yet, so I must not be done. What else do I need to do? Lisa?
You can look back to the denominator, you'll be able to cancel out things.
Okay. Guys, you need to be looking for difference of squares, right? And 1 minus x to the 4th is a difference of squares. It factors as, so I'm going to leave the numerator alone. The numerator is 1 plus x squared, and then 1 plus x. If you see a 1 minus x to the 4th, everybody needs to recognize that that's the same as 1 plus x squared times 1 minus x squared. And 1 minus x squared is 1 plus x times 1 minus x. I know a lot of you guys are already teaching classes, so you've been explaining this to your students. So don't mess it up for me, or I'll go tell them. If I can find out who they are.
I have to tell them to go to you.
It's just a regular test.
Okay, so with that, I can do some simplifying, right? What does that simplify to? 1 over 1 minus x, oh my goodness. Okay, so now what do I do with that?
That's just 1.
No, this is still a generating function expression. So what do I do with it? We got to close the deal here, guys. We're not done. What's h? How do we find h sub n? Nobody knows?
X to the n. X to the n.
Huh?
You just replace x with
No. We don't want to substitute. By the way, that's an important point. Don't substitute numbers for x, ever. Because then you have to start worrying about convergence issues. And in that case, some of this stuff doesn't even make sense. If you try to plug in x equals 1 way back over there where we had the red expression, if n is any number bigger than 1, it's going to blow up to infinity, and it's not going to make sense. So I don't want to plug a number in for x. What do I need to do with this, guys?
Doesn't that generate a bunch of ones, which is...
What do you mean? Okay, so when you say what doesn't it generate, what you mean is I can rewrite this again back in the non-closed